Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. Audio compression techniques were developed to better utilize our computing power and data transfer bandwidth of acoustic signals. In this video, we'll learn more about the creation of audio compression techniques and their intrinsic challenges.
So let's get started. To perform acoustic processing routines in real time requires compression of these signals. So if we have our acceleration signals mounted near the suspension, these will be correlated with road noise that passes through the suspension and then transmits into the body. These feed into the digital signal processor, which use microphones in the cabin as error sensors to ultimately play back canceling sounds through the audio system. This requires compression to make it happen, since the data bandwidth is very high. There is also an issue resulting from causality. The control of sound in the vehicle cabin requires that the error signal is a direct consequence of the noise, that this signal is received, processed, and sent to the control source faster than before the noise arrives at our ears. This is an issue given that all of this has to occur nearly instantaneously. All of this is to say is that there is a challenge in computing. The effectiveness of this noise control approach requires near instantaneous filtering, convolution, processing, and reproduction of the sound. This then creates a need for audio compression. Audio is often recorded at 44.1 kHz in 16-bit resolution per channel. This leads to 1,411 kilobits per second in bandwidth that's acquired for high-fidelity recordings, for instance, in a recording studio of artists. Now, a 3-minute song would be around 250 megabytes as a result of this bandwidth. But in practice, we know that most audio tracks are much smaller, typically around 2 to 4 megabits. So it's compression that helps alleviate such high bandwidth needs for data transfer, whether that's over the air or in an active noise control algorithm. Audio compression techniques are guided by masking phenomenon. Quieter sounds can be masked by louder sounds. For instance, we might not hear a phone ring if the vacuum is running in the house. And there are many other nuances to this phenomena when the level differences are less. But audio compression standards exploit these perceptual phenomena and remove extraneous audio signals that our brain cannot recognize. Let's use MP3 encodings as one example. The temporal recording is segmented into short time samples. A modified discrete cosine transform, or DCT, which is half as long as its FFT, is performed on the sample. Then, a 10-bit or 1024-point FFT is applied to the sample, after which another DCT is applied to that result. These DCT outputs are compared against psychoacoustic models of masking to eliminate extraneous signals that the humans would not hear. All of this is then converted back into the time domain from their frequency transforms. Let's look at one example. We have here an original high-quality recording shown in red, over top of which the MP3 encoding is shown in blue. The MP3 is encoded down to 128 kilobits per second. Let's zoom in on the data. Let's look at one case early on in the temporal series, where the levels are relatively small. We see that the peak of the original signal is always slightly more or less than that of the MP3 encoding. Likewise, even if the high amplitude sounds, the original recording is slightly greater than that of the MP3 reduction. This is indicative of the fact that fewer of the sinusoids or cosines are used in the reconstruction of the MP3 compared to the original signal. This is then justified through the audio recording sizes. The original audio recording in a WAV format had a size of 873 kilobits, whereas the 128 kilobits per second MP3 was only a 41 kilobit file size, a significant reduction despite not much reduction in the quality of the sound. Now, performing audio compression on pre-recorded data is relatively easy, but doing this in real time cannot leverage the benefits of the computing time that we have at our disposal when we sit down to process MP3s on our own. So the analog of audio compression when we do acoustic signal processing in real time is using limited samples. So consider a signal that's sampled at 44.1 kilohertz in 12-bit resolution. In other words, we have 4096 samples in each time segment. This will then be convolved with a 12-bit FIR filter that also has 4096 samples in it. So if we multiply the sample length with the sampling frequency, we find that each second there are 180 million instructions per second that the computer must process. That means the computer processor must have a power of at least 180 megahertz. But if we divide the sample length by the sampling frequency, we find that we're only reconstructing about 0.1 seconds of a room impulse response. We know that most spaces have reverberation that's longer than this time span. So there will be artifacts in our compressed audio signal that don't represent what was originally recorded. But if we crank up our signal length to a 16-bit value, where we have 65,536 samples per increment, we find that we have then a 1.5 second room impulse response. But if we do the calculation for the computing power required and multiply the sample length by the sampling frequency, we need a computer processor with at least 2.9 gigahertz power to process this high fidelity audio signal in real time. Now in practice, we don't even do this once per second. We might do this 10 times a second or 20 times a second. So this 2.9 gigahertz would need to be multiplied by 10 or 20 if we want to achieve very high temporal resolution in addition to frequency resolution. But there are many challenges to perform this in real time. Many applications need this real-time processing of acoustic signals: voice recognition, transparent headset listening, active noise control, head tracking spatial audio, and so on. There are multiple cases where these applications combine visual and oral cues. And if our acoustic real-time processor leads to audio delays of more than 20 milliseconds, people would recognize this through a loss of lip synchronization with the visual cues. And in fact, when we implement this, the A to D or analog to digital and D to A converters lead to basically a fixed 5 millisecond delay. So the encoder itself must be extremely streamlined to help us minimize the sound delay before our users recognize something is amiss.
And one of the icebreakers at these retreats was a game that was always a hit. And it was a game where somebody would tell a lie about themselves, and then a truth, and then another lie, and everybody would have to guess which one was the lie.
No, Johnny, they had to guess which one was the truth.
Which one was the lie?
It's just one lie.
What did I
You
say?
said two lies.
Well, it is two lies.
No.
No, the game is two truths and a lie.
It's true.
That's
So
the
you've
game.
heard of it.
Yeah,
You've heard
well,
of it.
yeah, because babies play that at their birthday parties.
Okay, whatever. It's a good game.
babies play
Okay?
it at
Now,
their birthday.
here's how it goes.
To summarize what we've learned, the inherent resolutions of human hearing and the inherent challenges of real-time processing of signals together motivate audio compression approaches. The MP3 compression algorithm exploits masking phenomenon to reduce unrecognized audio in a time series. Real-time compression occurs due to limited sampling and processing of incoming signals, since the output signal must arrive at the ear before synchronization is lost between the real-time environment and the audio playback.
That's it for this video. In the development of audio compression techniques, the human perceptual phenomenon of masking is exploited to reduce the data encapsulated in the compressed audio signal. In the next video, we'll learn more about this masking phenomenon and how we may not perceive sounds that we hear.